So this is lesson 7.5, and we're going to be dealing with rational expressions. You can see simplify, which is what we'll spend a bulk of our time here on. Add, subtract, multiply, divide, radical expressions. You did that in Algebra 1. We didn't spend a lot of time on it though, so we probably need to plow through it just a little bit. First of all, the square root of 3 times the square root of 3 is the square root of 9. What's the square root of 9? 3. The principal square root is 3. This one, we have this 1 plus the square root of 2 times 1 minus the square root of 2. Now you might can predict a little thing here because these are conjugates. This is going to clean up some of the nasty that we have going on here. But this is, for all intent and purposes, it's like a binomial times a binomial. It's not technically, but it's a binomial times a binomial. So we're going to use FOIL. So first, 1 times 1. Outside, 1 times a negative square root of 2 is negative square root of 2. Inside, square root of 2 times 1 is positive, right? And then the last one in each bubble, the square root of 2 times the negative of the square root of 2, which is the negative square root of 4. So you can see what happens to these two guys in the middle. They're going to cancel. And that 1 minus 2, because that would be 2, right? So that 1 minus 2 is negative 1. You can always back the video up and watch it again if you didn't get that. So let's talk about this one. In the previous lesson, we looked at things like the square root of b to the 4th. Or we looked at the 4th root of b to the 4th. And we talked about the O McDonald, exponent divided by index. And that would be b squared, and that would just be b. Technically, it would be the absolute value of b because you have even, even, odd. But that's how that would work. Well, the problem with this one is, when you think of the 9 divided by 2, it didn't come out even. Because those all came out even in that other lesson. They all came out even. It's beautiful. But that doesn't come out even. Now, if I do the 4 divided by 2, it's good. You know, I know what the square root of 25 is, by the way. Right? I know what that is. But let me just take a second and rewrite this whole problem. Because I'm going to write the 25 as 5 squared. Because it's what it is. I have a reason for doing that, just as a point of order here. And this a to the 4th, which is going to be no problem because 4 divided by 2 is going to work out beautifully. It's the b to the 9th that's the problem because 9 divided by 2 doesn't work when we do our O McDonald, exponent divided by index. So I'm going to call b to the 9th b to the 8th times b. First of all, do you agree that b to the 8th times b is b to the 9th? Yes, yes, and yes. Now the beauty of that is that's a square, and that's a square. So I'll be able to take those out really easily as square roots. So you can see the 5 to the 2 divided by 2 is 5 to the 1. A to the 4 divided by 2, a to the 2nd. B to the 8 divided by 2, b to the 4th. And then the square root of b is just the square root of b, and that's just how it works. It's just how it works. He can't come out. He's not a square. Only the squares get to come out and play. So you can see somebody worked through that, got the same answer, maybe a little slightly different process than I had. And so we do the cube root. The cube root. Now, in this particular problem, that's not going to be a problem because you can think of 125 as 5 cubed, which is going to be good because then the index, or the exponent divided by index, is going to come out even. The m to the 30th, no problem because the exponent divided by index can come out even. But the 20 divided by does not come out even. So I'm going to have to rewrite the p as p to the 18th times p squared. Does everybody see why I got p to the 18th? Because it's a multiple of 3. And then p to the 18th times p to the 2nd is p to the 20th. So that's how come I got a p2 here. Because I had a p18 here because that's a multiple of 3. So when I clean that up, all of these are cubes. That's a cube, that's a cube, that's a cube, that's not a cube. He can't come out. So the exponent divided by index, 5 to the 1. exponent divided by index, m to the 10th. Exponent divided by index, p to the 6th. And then we're gonna have the cube root of p squared. Just how it was. Sometimes it doesn't come out even. And so somebody worked through this, they got the same answer we just got. By the way, without anybody here to correct me, I don't know what I'm gonna do when I make a mistake. And there's nobody here to fix that for me. Just gonna plow through those. If you deal with the quotient, first of all, the square root of 27 divided by the square root of 3 is the square root of 9, because 27 divided by 3, you got square root and square root. It's great, it works really nice. If you've already got it written as one fraction, you can split it apart and work with each piece individually or independently. And we'll see that with a couple things that we do. This one. So simplify expressions with the quotient property. If these were the same letter, then you could work inside the radical and see what y to the 8th divided by y to the 7th is, but they're not both y, they're one of each. And so we can't do that. And also the harsh part of this, which is unfortunate because it's the first example they give us here, but the harsh part of this is the denominator is not going to be cubed. Because when you do the 7 exponent divided by the index 2, it doesn't come out even. 7 divided by 2 doesn't come out even. So we've got a problem here because it doesn't come out nice and cute the way we'd like for it to. So we have to do something. It was in the slide earlier. We have to do something called rationalizing the denominator. And we looked at that in geometry a little bit. We talked about some stuff in geometry. And we talked about some stuff in chapter 5 when we were doing imaginaries, because we use complex conjugates to make that denominator not be so weird, to make it real. And here we'd like it to be something besides some radical thing. Because if I simplify the square root of x to the 7th, I'm going to get the square root of x to the 6th times x, right? That's what I would get. And so then that would be 6 divided by 2, be x cubed. But then I still have the square. I still have a radical in my denominator. I don't want a radical in my denominator. I want my denominator to be something nice and cute, because where you're going, the math world you're going into, you may have to take that and then find common denominator, and you don't want to find common denominator with the square root. So we want to make that denominator not irrational. So we call it rationalizing the denominator. So we're going to rationalize this denominator by multiplying the numerator and denominator by something which, remember the terminology, a fancy one. So I'm going to multiply both of them by x, but that's really just 1, not x, the square root of x. That's really just 1. That's a fancy 1. And you can multiply with 1 all day long and not change the value of a thing. So if I do that, numerator, I get this. You might put the x first if you're thinking of order of the letters, but I'm just going to leave it like that because of where I'm going. And the square root of x to the 8th. Now, look what happens to my denominator. It'd be x to the 4th, wouldn't it? Because exponent divided by index. Oh, McDonald. E-I-E-I-O. And so we'd have that easy in the denominator. In the numerator, it'd be y to the 4th times the square root of x. In other words, even though this doesn't look any less complicated than that, in fact, it might look more complicated, but the beautiful part about this as opposed to that is now I would have an easy time finding some polynomial common denominator that I could merge fractions with if I'm adding and subtracting and doing stuff like that. And that's where you're going. That's what you're going to see in your future. And so you can see that that's what happens here. There's my fancy 1. They went ahead and cleaned it up and then did the fancy 1. I just did it up front, and they got the same answer that we did. So cube root, you can't take the cube root of 2, you can't take the cube root of 9, you can't take the cube root of x. None of those. So I'm going to multiply by a fancy 1. So I'm just going to put a multiplication in a fancy 1. I'm going to multiply the cube root of something times the cube root of that same something. Remember, it's not the numerator I'm trying to fix, it's the denominator I'm trying to fix. So the denominator is my focus. Whatever happens to the numerator is just happens to the numerator. I don't care. Doesn't matter to me. So I'm going to multiply this by 3, because that's going to give me 9 times 3, which is 27, which is a cube, so I can do the cube root really easily. And we'll multiply it by x squared, because x times x squared is x cubed, and then the exponent divided by the index work out real nice. So I'm gonna do the same thing to the numerator so that I have a fancy 1 here. Any number divided by itself is just 1, so I'm really just multiplying by 1. So you can see how I've got the numerators here, denominators here. So numerator, I get the cube root of 6x squared, which will not simplify, because you don't know the cube root of 6, you don't know the cube, 2 divided by 3 doesn't come out even, and that's it. And the denominator is the cube root of 27x cubed. So the numerator, as I said, can't do anything with that, you just can't. Not in this case, sometimes you can, but you can't in this case. But the cube root of 27 is 3, and the cube root of x cubed, because 3 divided by 3 is just x. And don't be trying to cancel that, because that's a regular x, that's the square root of cube root of an x squared. You can't do that, you just can't do it, you can't do it. So that's just the answer to that one. I guess we should have shown you the answer, but yeah, that's the answer to that one. Simplifying radicals, multiplication of radicals in this case. So we have a cube root times a cube root. So our coefficient 5 times our coefficient 1, and then the cube root. 100 times 10 is 1,000, and a squared times a is a cubed. Now that's great. You know why? Because the cube root of 1,000 is 10. 10 times 10 times 10 is 1,000. So the cube root of 1,000 is 10, makes that 50. And the cube root of a cubed, remember the exponent divided by the index, be a to the first. And that's the answer. That cleaned up nice. They don't always, but that did. Cleaned up really nice. 58. Now the cube rooty problem. Coefficients, 6. And then the cube root of 16 times 4, which is 64. And a cubed times a, a squared times a, which is a cubed. And that works out real nice because those are both cubes. Because that's 4 cubed. 4 times 4 times 4 is 64. So you do the cube root of 64, you get 4, makes that 24. And then the cube root of the a cubed would be a, so it's 24a, making the answer B. In Algebra 1, we talked about addition and subtraction of radicals. If you've got 2 of them square roots of 5 laying on your desk and somebody comes along and gives you 3 more of them, adds 3 more of them square roots of 5 to your desk, guess what you got on your desk? You've got 5 of them square roots of 5 on your desk. Is that logical? I hope. If you've got 4 of them square roots of 3 on your desk and somebody says, I want one, and they come by and they steal one of your square roots of 3, wah, then what have you got left on your desk? 3 of them square roots of 3. That's what you got left on your desk. So that's how that works. What we're doing here is keeping our radical, and one of the things that we said in Algebra 1 is we have to have like radicals. So it has to be the square root of 5, the square root of 5, the square root of 3, the square root of 3. You can't be doing a square root of 3 plus the square root of 5 and make the square root of 8 or something weird. You can't do it. So it has to be, but what you do is you keep the radical, work with the coefficients. In this case, we're adding them. In this case, we're subtracting them. So again, this is Algebra 1. This is Algebra 1. We would have done this in Algebra 1. None of those are like radicals. They're all square roots, true enough, but the radicands are different. 45, 80, 20, they're all different. But I think we can clean this up a little bit because 45 happens to be 9 times 5. Now 45 is also 3 times 15. It's just that don't help because 3 is not a square, 15 is not a square, but 9 is a square. That's good. And 80 is 16 times 5. And that's good because 16 is a square. I mean, 80, call it, 2 times 40 or 4 times 20. But that doesn't help because they're Neither one of those are a square. That's a square, but it's not the biggest square. That's the biggest square in 80. And then the last piece, we have the square root of 20, which is 4 times 5. Okay, so what I did was I found the square hiding in there in all 3 of my radicals. Sometimes you can't find them in all 3, sometimes you can. So in this case, you can. And so when we simplify this, square root of 9 is 3, put it with the other 3, 3 times 3 is 9. Square root of 16 is 4, times the 5 is 20. Remember, square root of 5 you can't simplify, so he stays in the house. He's not a square, you don't come out. And then the square root of 4 is 2, makes that 8, times square root of 5. Now look, square root of 5, square root of 5, square root of 5, they're all like radicals. They have the same radicand and the same index, so they're like radicals. And so 9 of them fellers minus 20 of them fellers plus 8 of them fellers, negative 3. You do 9 minus 20, you get negative 11. Negative 11 plus 8 is negative 3 of them square roots of 5. And then we have multiplication. In this case, we have what appears to be a binomial. Technically it's not, but it appears to be a binomial. So we have, 2 things times 2 things is multiplication. So we're going to use our friend FOIL. In FOIL, it's the first one times the first one. So look, this is 2 times the square root of 3 times a normal 3. So this 3 times this 2 is 6 with the square root of 3. Then we do the outside. Then we do the outside, that's the 2 furthest apart. So you can see positive times negative, 2 times 1 is negative 2. And the square root of 3 times the square root of 3 is the square root of 9. I'll come back to that. Then the inside, the 2 closest together, remember that's a regular 3 times that regular 3. That's not a regular 3 times the square root of 5. It wouldn't work, but a regular 3 times a regular 3 is a regular 9 with the square root of 5. And then the last one in each bubble, that's 3 times a negative 1. And the square root of 5 times the square root of 3. So you can put the radicands together. We saw that previously. It's 15. Now, this cleans up because it's just 3, right? It's just 3. But none of the others are like radicals because you got the square root of 3, the square root of 5, the square root of 15. You can't find any squares hiding in there. So ends up, the final answer is just 6 times the square root of 3. That would be 3, make that minus 6, plus 9 times the square root of 5, minus 3 times the square root of 15. There might be some place in the world where you want to put the regular number, the integer out here on the end by itself and have all them radical people over there together, but that's the answer. The pieces and parts may be moved around, but that's the answer. Let's see, they did FOIL, and they left their 6 over there where I did mine, so same answer. These are just practices of the same stuff, and I believe that's it.